Hey Menas, it's very nice to meet you here in Greece.
Hi, Sky. Glad to meet you in person.
It's like 2 years we plan to do this, or three. Or
Yeah,
I think.
we're talking for a long time, right?
Yeah, Gino, you tried to introduce us like in 2017. Yeah, now it finally happened. It's very nice. We talked yesterday. It was very nice. We agreed on a lot of things. I was very surprised that you agree with that there's something wrong with inflation theory, and I was very surprised at that. I thought that yeah. And we talked about my model that the universe might be much older if we assume a constant acceleration, quadratic function, because then at the beginning it would be very slow. And I think the only reason why they have to assume that it was very fast at the beginning is because otherwise it would collapse back. But I agree with Newton's assumption. He was asked why doesn't the universe collapse, and he said it's because the universe is infinite, so their gravity cancels out because there's a pull from every direction.
Right.
Yeah. And you did a lot of cosmology too. You actually started with astrophysics first, and then you went into consciousness also.
Yeah, I first started with, I studied with Phil Morrison from MIT. So my main thesis, my main topic and thesis was supernova explosions.
I studied a lot supernova, yeah.
Supernova, not the process of explosion itself, but the effects of supernova on interstellar medium. Phil Morrison was my advisor. He was a famous MIT professor in that. And by the way, he worked on the atomic bomb that was dropped on Hiroshima.
Well, most physicists did. It actually set off the black hole research for 10
right.
years.
Yeah, that's true. J. Robert Oppenheimer.
Yeah, he was the main person.
Main person, and Morrison was his student. And anyway, after what Phil, he called him Phil, saw what happened to Hiroshima, or Hiroshima, whatever, however you want to announce it, he said, no more of this, and he went to astrophysics.
You know, I did something about supernova. I looked at the luminosity of supernova, and I wanted to check if it drops with the square of the distance. And I used Einstein's theory, Einstein's distances, which means you have to have a different equation for different redshifts. For less than 0.2 redshift, you use one equation and then another and then another.
Right.
And in my theory, I have just one equation for all the scales, and I want to see if that is justified. And so I checked with my equation and the mainstream equation, and I figured that with my equation you get a perfect fit. I calculated a average luminosity star and imagined that I take it further and further away, and how the apparent luminosity or apparent magnitude would decrease. And I superimposed that on the graph I had from the actual data, and then there was a perfect fit. But with Einstein, it was quite a misfit. And that problem is actually known, the very faint supernova.
Yeah.
I mean, you know that for sure. And, and it's also part of the whole thing about the accelerating universe that has to do with supernova, because the supernova were too faint in general. And
in the past.
In the past, yeah, in the very large distances, and I cannot strictly prove that my equation is correct for the distances. I can only prove that it must depend on only one equation and not many different. So I can prove that it must be simple. But then there's evidence that my equation is correct, because it is the closest to the theoretically expected magnitude or luminosity of supernova. So I think that the expansion of the universe was accelerated, and also makes sense, because then it can be an entropic expansion, which is basically saying that the expansion of the universe cancels out the entropy increase in black holes, because black hole entropy depends on the surface area.
Right.
And so that's something to the power of 2, so it's its surface, and so it makes sense that the expansion, if it's leveling out that, it should also be a quadratic function. Yeah.
So,
But that doesn't mean that there's. I don't believe that there's a black hole with a event horizon. I believe that it's a quasi black hole because we have seen that most black holes, or basically every supermassive black hole, has very strong magnetic fields, and that means it cannot have an horizon. With a horizon, moving charges wouldn't generate a magnetic field because it's cut off with event horizon.
right.
It's quite similar to how it is with the speed of light. When you try to get closer and closer to the speed of light, you can get infinitely close, but you can never reach it. So I say it's similar to when you fall into a black hole, then you can also never reach. And it's quite amazing that recently I saw this interview between Jordan Peterson and Roger Penrose, and Jordan Peterson was pressing him really hard on that. But isn't it that you actually freeze in front of the event horizon? And Roger Penrose basically tried to distract from that by saying, "Oh yeah, but you." No, he didn't say yeah. He said, "Well, your image fades away, and then if the image fades away, then maybe you don't need to worry about that." I was thinking.
So, yeah, actually, Morrison did quite a bit of work on spinors. They were called spinors back then, which were supermassive objects that were not black holes, and they had strong magnetic field. Spinors, S-P-I-N-O-R, spinors. They went out of fashion, and in my case, I work on black holes, but I didn't work on. I work basically on Kerr black holes, not the
rotating black holes.
Yeah, rotating black holes, not the Newman black holes that have magnetic fields. But as you said, because of the accretion.
Newman black holes have electric charge.
Right.
So, yeah, I was just talking about magnetic.
Yeah, but moving electric charges will generate magnetic fields.
Yeah, but the Newman black hole doesn't violate any the no-hair theorem. What I say violates it because it's the.
I see. Yeah. Well,
it's the original.
So
from the original star, actually.
So actually, the original star must have had a magnetic field.
Yeah,
and,
but that would have disappeared after the event horizon formed. And then if you to give it new charge, then you cannot charge it.
So there are some mysteries there about black holes. I mean, one of the big mysteries that, and we can talk about other things, that seems to still be there is how come there is directed motion, these jets, away from black hole, from supermassive black holes.
Is that a mystery?
What causes these jets to come out? They're not easy to form. There's jets that come like this.
Isn't it similar to a neutron star where the charged particles collide and you get a jet?
Yeah, but neutron stars have a surface. They are, they have magnetic fields. They have surface.
So you say the jets also would suggest that there should be
something going on in terms of somehow.
There are many others who actually have models of black holes not being the classical black holes. There's Abbas Mitras, which I know him very well.
Right.
And he says that there's Eddington radiation, which somehow stops the collapse. Yeah.
Right.
And that Eddington radiation, it reaches some critical level. I think in essence it's very similar to how I deal with it by saying that time dilation is so much that you can't get a black hole. I mean, if from the perspective of all pre-existing observers there's no real black hole, but just a quasi-black hole, then that should be the answer. You shouldn't. It doesn't make sense to say you can go around the corner in space-time because quantum mechanics requires to have a present, and I think that's something you emphasize a lot, that because of quantum entanglement and how the past is decided in the present, so that suggests that the present is actually quite special, and
right.
Yeah, and there must be some frame of reference in which is that present on which that present is based on. And that can be many different things.
Which it bothered Einstein also a lot. I mean, he actually, before developing theory of relativity, he was interested very much in the Mach's principle. He was influenced a lot by Mach's principle, which is, I think it's...
He thought that he didn't realize it well enough?
Well, he thought it was crucial, and, and of course, Mach thought that the masses of the particles or the masses of matter are determined by the large-scale structure of the universe.
Yeah, yeah.
So you have
Relationism.
yeah. So you have the entire universe mass determines the local mass, which is a very interesting, point of view. And still today we don't know why the masses of the particles are what they are, right?
Well, my idea on that is very, very old. It's not my idea actually. It's called the electromagnetic mass theory, and that's actually what led to relativity, because before Einstein, people already had written E equals mc squared, just with the wrong factor in front of it, and basically they were calculating how much energy is there in the electric field of an electron, and they came up with exactly half the mass of the electron, and then some arguments were made to say actually when it moves, that's the whole mass of the electron.
Right.
So, but the problem with that is that I made some calculations on that, and the problem is that it's a bit self-referential, because you need the classical electron radius in
Right.
order to calculate it.
And there's no such thing really to speak of. Classical electron radius.
So it's tricky, but that's a very technical
So
topic.
that's actually, there's still some mysteries there in terms of black holes, and we know they're collapsed objects, but how collapsed are they?
Einstein actually said that the black hole would be prevented because when the star collapses, it will rotate close to the speed of light, and that would prevent the collapse. And then there's
Yeah, in fact, those black holes, they're spinning with essentially the speed of light, but not quite. They're spinning with 0.998, if I remember correctly.
and then there's somebody called what is his name? George something. He says that when you go inside the black hole, then mass becomes negative. But actually, it should be imaginary, because if you run the equation, you find it's imaginary. I don't know why he says negatively somehow. He wants to make it seem like that's dark energy. So that's dark energy star theory. I think that's how it's called, yeah. And so that's a little bit that's a little bit similar to my theory, because it says it's black holes causing the expansion of the universe. So maybe that's the closest to my theory. But it's not really. I'm not really agreeing with it, because he's still pretending that there's an event horizon. He just says, okay, you cannot penetrate it, but it's there. He doesn't realize that you cannot. That the star itself has to fall into the horizon, into that trapped surface. So if you realize that, then there can't be not this horizon.
So
there are other horizon. There's at 2.2 of the Rothschild radius. You cannot receive light anymore, any visible light here, which is kind of important in my theory, because it's very much based on consciousness. So it matters a lot what actually people and animals.
So actually, it's interesting to go back to Einstein and find out why he didn't believe that black holes would form. The guy was very smart. We should see what exactly he meant. But anyway, okay, so that's black holes. Of course, there are collapsed objects, and whether they're, as I said, my advisors, Morrison thought that they're spinners. He didn't quite.
That's quite interesting.
He didn't quite believe in black holes. He believed in magnetized supermassive stars. That's what he believed.
Yeah,
I mean, spinners are basically like pulsars, but they're big stars.
Yeah, my elementary spaces, my atoms of space, quantized space, they're actually inspired by black holes and spinners. I mean, it's inspired by twistor theory, and basically point particle theorists, they say that particles are points, but then they must be black holes. And then I thought, okay, they can't eat anything. What if we construct a granular space out of overlapping surfaces? But then I thought, okay, they're too small. If you have one virtual particle every Planck length, then they cannot overlap. So I thought, okay, I have to scale them up. How much? I used the coupling constants of electromagnetism and gravity, so I scale it up to the strength of electromagnetism. So then you can have larger atoms of space. So when they overlap, they form something that feels like 3D, but it's based on these 2D surfaces.
I see. I guess there's a rich area to revisit would be to ask about the feasibility of collapse to black holes, and and we know that there are collapsed objects because we see them in astrophysics.
Yeah.
We know there are pulsars, with neutron stars, and we know there are white dwarfs. So we know that there is an end state of evolution of what eventually, when they run out of thermonuclear fuel, they collapse. As I said, Phil Morrison, maybe the guy was right. Phil Morrison believed in spinors. Spinors? Let's see. Roger Penrose was a spinor, right? With
spinor, and then the second step was twisters.
Right.
One dimension.
Okay, so no, the Morrison was called them spinors, or basically they are magnetized stars, so there are massive stars that they have magnetic fields. They're collapsed, right? They're collapsed in some ways, but they are not.
Can't be reversed. At the beginning, people thought that maybe when the star collapses, maybe the different sides of the star will miss each other because it's not symmetrical.
Right.
Maybe they come out the other side. And Penrose solved that with the singularity theorem, which I don't agree with, but it's still kind of useful because if you change it slightly, you can say, okay, he said that if you have a ring with a critical circumference, and if you can pull that ring over the star, then it must become a black hole. And I say it cannot enter this ring. So that's the minimal. So regardless of the shape.
I think what is discussed.
I'm just trying to save his theorem a little bit.
Well, I think what's I worked a lot on black holes, so I like them. But I guess we have to go back to the physics of collapse. I think that's an important thing. Once you have a collapsed black hole with short shell or parametric, well, that's more or less what you're going to get.
Even a quasi-black hole is almost the same like a normal
That's
classical
right.
black hole. Just the magnetic field is different.
But the magnetic field is a problem, and
you still have radiation. You don't have information paradox because it's still shining. It's just all redshifted.
Correct. And so that.
And it has a temperature, so you have thermodynamics. You don't have any of the problems. And I mean, if you have a true black hole and you have Hawking radiation, then you run into a huge issue because they say, okay, it can evaporate away, and then how is the entropy not gone? And the excuse people give is, oh, well, the Hawking photons, they go into random directions, and that's why the entropy is still higher. But that's not non-controversial. I mean, Roger Penrose, for example, in his book, he says, oh, well, after the black hole evaporated, you have to recalibrate the entropy, reset the entropy somehow. So it's not a small issue or something.
So it's a hand waving. And of course, as we know, Roger Penrose himself, he's asking how come you have objects with very high entropy, right? Mm-hmm. How come the universe that has very high entropy, it's a black hole,
yes.
becomes
this issue doesn't exist in my theory because in my theory the entropy was always high because I start off with a lot of primordial black holes. And how do I get them? I mean, my theory doesn't have dark matter because I have this very old universe, 42 trillion years old, and it's natural that 90% of the stars are burned out. So I don't have the classical dark matter that we identify with the missing matter in star surveys, but I have something similar to dark matter because I have complex mass, and so there's a real component and imaginary component to mass. And so if the imaginary component becomes negative, you have an antiparticle. When it's positive, you have a normal particle. And when the real part becomes negative, you have exotic matter. And we don't find exotic matter anywhere here.
We don't find it.
But in my theory, exotic matter would still have positive gravity because in my theory, I have all these bubbles, these elementary spaces. So Earth has a lot of charges, and all the charges, they emit virtual photons and virtual gluons. So if the density is higher here, then more pathways lead through that region of space. So that's gravity, and in this scheme you cannot have something negative. You cannot have negative gravity. So if you have exotic matter, basically what happens, and I also think that happens with dark matter in general, in any theory, should happen. If it's cold, then it should collapse immediately to small black holes, primordial black holes. And I mean, if it's not cold, then it's useless, because then it will just fly everywhere, and it's not interacting, so it will not have a gravitational effect.
So that's another issue that we need to bring into astrophysics. I'm not sure how much it has to do with quantum physics. The problem of dark matter. I mean, we just don't find it.
Yeah, now they want to do another experiment at the LHC, like after 40 years of
Oh,
not
man.
finding something. That's the next experiment.
Yeah, they're going to keep pumping money into this.
Yeah.
I sort of predict I'm not going to find it. I guess
That's not a risky prediction.
I don't think it's a risky prediction, but
You
why?
can try to find somebody to bet with, but I think they don't want to bet with you.
They don't want to bet, but the point is, okay, guys, how much money you're going to be spending on finding something that absolutely we actually absolutely have no. No, I'm being now unorthodox. We have no direct evidence other than the peculiar motions of stars in the galaxy, and Zwicky, the famous astronomer Zwicky, way back.
He came up with dark matter.
Well, he said something's wrong here. He said there's
Missing matter.
There's basically something missing matter. There's non-Keplerian. There's
Non-Keplerian motion.
Yeah, non-Keplerian motions. There must be something there, and in fact, one of the ideas I had, but I never put it down in print, is what if the galaxies, trying to save everything, what if the galaxies are not actually virial? They have not achieved, Keplerian orbits. If they have not achieved Keplerian orbits, then the dark matter disappears.
Yeah, we certainly don't have Keplerian orbits outside of the local group. I mean, the very curious thing is that I found out recently is that I was expecting that beyond the local group, you should see expansion, but you have to get out much further.
Far away.
200 million light years.
200 megaparsecs, whatever. 200 million light years, whatever.
Yeah, 200 million light years. And the thing is, at that distance, you don't have the independent distance measures anymore. You have them until that point. So we don't have independent distance measures for the distances where actually
well, that's the other
expansion
thing.
takes place. Really.
That's actually the other thing about that. We don't really have independent yardsticks. We have them locally, very locally, but you don't have them all the way out there.
Yeah.
And then, of course, the whole issue of luminosity of quasars. Is are there standard candles or they're not standard candles? I think
variation is quite big. Yeah.
Right. I think all
you
this.
have to look at the logarithm to have it orderly.
Correct.
And neat.
So there are some still very big mysteries in cosmology, and I would say it starts with so-called dark matter. Where is it, guys? And what is it made of? And
what I found is that I looked at how much expansion redshift you should have in different positions, and I thought if a galaxy has less redshift even than the expansion redshift should be, that's sort of violating Hubble expansion, homogeneous expansion. So I call those galaxies outlaws. So I found one in the mid, somewhere in the distance of the Andromeda galaxy, and then 5 other at the border, 4 other I think, and then when you go beyond that, you find another 38. And so, but those are not, in my theory, they are not outlaws, because in my theory, expansion is not homogeneous, it depends on entropy. And so, in my theory, none of them are outlaws, they're all fine.
Yeah.
I also looked at all the different Hubble values that ever were proposed in the last 20 years to see if you can reduce the outlaws, but you cannot reduce them significantly. Maybe get rid of 5 or some few. Yeah. So, but the argument in the mainstream is if you have a gravitationally bound system, then you shouldn't expect expansion redshift, because if things are not moving apart, then there will be no expansion redshift. but it doesn't quite fit the assumption that, I mean, it's usually explained always that when light travels through the universe, the expansion stretches it out. So why should it be stretched out only after it leaves the local group or after it leaves the Lacania group or something? Like, how far you have to go until it can actually, it's legal. They claim some sort of expansion Doppler duality that every expansion redshift must at the same time be a Doppler redshift. But I think that doesn't make sense. It has a lot to do with the assumption that energy is relative. And so the universe is expanding and the CMB is losing energy, but they try to claim that this is not a loss of energy because it's somehow relative, because if you move towards the light, then it will change its energy. But I mean, at the beginning they were hoping that the universe will collapse again so that the universe gets its energy back, and now they know that it's not possible because the universe is getting faster and faster. So the only way out seems to be now that to say that it's somehow relative. I mean, how can I restore the energy of the CMB? I cannot fly into all directions at the same time so that the CMB